Hello, good morning, everybody. So, as you all know, that this is the first QEEE session on control system, and within this control system, we would be studying this one specific topic called the stability analysis. So, overall contents of this topic, we'll start with the introduction and origin of stability analysis, that from where the stability analysis or the study of the stability analysis has been originated. Then we will see some definitions of stability, that how this stability is defined, how we compute the stability or how we determine the stability of a given system. Then we'll see the number of feedback structures, different feedback structure to study the stability. Then there are a number of tools by which we can do the stability analysis. So the first with which we'll start with is the Routh-Hurwitz criteria. Then in the state space, using the locus method, Bode plot, and finally the Nyquist criteria. If the time persists, we will also see the robust stability, which is much more deeper concept than whatever the stability analysis what we'll do in the above. So the overall learning outcomes of all these 6 hours of lecture, that you would be able to understand the concept of basic stability of dynamical systems, that how you define, how do you compute. You would be aware of the key concepts of the absolute and relative stability. We will also see when do you say that the system is marginally stable. You would also be familiar with the notion of bounded input, bounded stability. We'll also see the relationship of the S-plane pole locations, basically for the transfer function models, and of the eigenvalue locations, which are basically computed for the state variables models to system stability. We'll come on to this more specifically, because when you define a model of the system, there are a number of ways you can represent system, either in the transfer function or state variable or in any other function. So when you speak about the transfer function models, you compute the location, pole locations in the S-plane. When you speak about the state variable models, you compute the eigenvalues. So we'll also see that how do you represent the state variable models. You will also get to know how to construct the Routh array and how you use that array to compute or determine the stability. Then we'll also see the Nyquist stability criteria and the role of the Nyquist plot. We will also be able to see the relative stability with respect to the phase and gain margin. And finally, the last one, which we will introduce at the very base today also, the gang of four, what we say the sensitivity functions. So this is the much more important concept when you speak about the stability. So the references for all these 6 lectures, which I would be or which you could also refer after the lectures. The first one is a Norman-Nice book, Control System Engineering. The second is an online book by Carl Ostrom and Richard Murray. So this book is freely available on their website. You can download freely. And the third one is basically an article in the recent Control System magazines, which is on origin of stability analysis, governors. So all this, the last 2 references are you could easily download. I suppose the first one would be available in your library. So you could refer all these 3 references if you want to study later on after the lecture. So now the question arises, from where the stability analysis is originated. In this figure, what do you see? Basically, it is called a governor. This is one of the very basic feedback control loop in the modern Europe, or let's say one of the very first feedback control system. So first we'll see that so this is what you call the governor. Okay, this is the very first feedback control loop which was invented by James Watt, and on the right hand side figure, it's a basic improved version of this governor. So the very basic function of this governor goes, when this disk D starts rotating, these 2 balls starts being apart from each other. So whenever it expands, whenever it start expanding, these pulley will pull down, and in turn this pulley will turn up basic, and then finally closes this wall, what do you call the wall. Okay, so this is basically a control as well. So now how it is used to control the flow of the fuel. So the basic, so what we want to see, the actual speed. Let's say we have a what do you call the motor is attached at the bottom part at this side, of which we want to control the speed. So whenever the actual speed increases beyond the desired value, the increase in the centrifugal force of the flyball governor. So whenever the speed of this flyball governor increases, like I said, these 2 balls will start apart from each other. Okay, when they will start apart, okay, this wall will close, meaning to say the flow of the fuel will, okay, basically the closing of the steam valve, finally resulting in the supply of less steam, and then the speed of the steam engine decreases, right? If the speed of the motor drops below the desired value, the opposite the opposite action occurs. So on the left hand side, like I said, is given as the original design, which has only one fly ball, and on the right hand side there are two fly ball, which is a much more improved version. So how this governor helps us, or why this stability analysis required for this governor? Like I said, this is one of the very first feedback control loop in the modern Europe. So when at the height of industrial revolution around this 1868, many governors were installed to control the speed of the motor. Okay, so when all these governors were installed in a high capacity, it was observed that these feedback control loop were not behaving in the desired way, which was expected from them to behave. Okay, so there were some issues like instability, inaccuracy, and which were not incurred by either theoretical or practical approaches, right? Because this is a mechanical device. Then finally, this in the Maxwell 1868 paper, he discussed about the stability concept. He laid down the simple mathematical models for these governors, for the motion of governors. He also highlighted the importance of integral actions. Then comes on to the linearization. Why this linearization required? Because when he derived the simple mathematical models, they were non-linear in nature. So he linearized those models to study the stability of that system. So he address the stability is nothing but an algebraic problem. Okay, we will come on to this, that how it is defined as an algebraic problem. So he gave the stability criteria only for the first, second, and third order systems. If this concept of first of order system, nth order system is not clear to you, we will come on to this also, that how, when do we call that it's a first, second, or third order system. So he was only able to give the stability criteria limited to up to third order systems. Subsequently, he also posed the stability problem in competition. He solved the stability problem up to third order system. Then he also posed that how the stability problem can be solved, or how it can be solved for basically the nth order system. Okay, we'll come on to this all these issues one by one. So what he says, that it will be seen, pay close attention to the statement. This was the exact statement which was copied from his paper, 1868 paper. It will be seen that the motion of a machine with its governor consists in general of a uniform motion. He wants the motion of the governor a uniform motion without any response going behaving weirdly, combined with a disturbance which may be expressed as the sum of several component motions. I will repeat this statement once again. It will be seen that the motion of a machine with its governor, why he speak about the governor? Because in the current system the governor is basically a controller. Okay, with its governor consists in general of a uniform motion combined with a disturbance which may be expressed as a sum of several component motions. So whenever a disturbance starts acting on this governor, or as a on the whole system, that what type of responses we will going to be observed. These components may be of four different kinds. The first, the disturbance may continually increase. So what? Okay, it may continually diminish. Third, it may be an oscillation of continually increasing amplitude. I will start. I will. Okay, let's first see that how it can you can visualize this very first point. The disturbance may continually increase. So let's say if I have this axis, okay, the disturbance may continually increase, either exponentially, either straight, or in any fashion, but it should be continually increasing. Okay, this is our first point. The second says it may continually diminish. Okay, the exact opposite to this one. Okay, we'll come on to this, that or we can see also at this point that this is the time axis, the x-axis, and these are the responses. Okay, third, it says it may be an oscillation of continually increasing amplitude. So let's say if this is the third one, oscillation with the increasing amplitude. So if I start from this, all the these oscillations, okay, you see there are oscillation and they are continuously increasing. The fourth one says continuous oscillation of decreasing amplitude. The opposite of this one, there are some oscillations, but they are of decreasing amplitude. Okay, So these are the four components which we visualize. So now when we speak about the basic stability concept, just by visualizing the responses, it comes to us the first and the third cases. The first and the third cases are evidently inconsistent with the stability of motion. Why? Because if you see here, the response is continuously increasing. So at when the time t tends to infinity, the response will hit to infinity, right? For this case and for this case as well. And opposite to these 2 and 4 shows that our system is stable when we visualize just the responses. Okay, we haven't done so far any computation, but we'll come on to that. Okay, and the second and fourth alone are admissible in a good governor. So what does it mean? This condition is mathematically equivalent to the condition that all the possible roots, that is real, and all the possible parts of the impossible roots of a certain equation shall be negative when we say that the system is stable. So basically the second and fourth condition is mathematically equivalent to the condition that all the possible roots. So what do you mean by this possible roots? We'll come on to this, but just to introduce at this point. So here we are speaking roots in the S plane. So you know that when we speak about the S plane, this is our real axis and this is our j omega axis. Okay. So when I say the roots, I mean to say the real part. So this is what you call the real axis. This is your real axis. This is your imaginary axis. So this condition is mathematically equivalent to the condition that all the possible roots, pay attention to this statement once again, that all the possible roots, the real roots, and all the possible parts of the impossible roots. So if the roots are real, then we just need to take care about the real part, of course. But when the roots are complex, meaning to say let's say I have a root defined by p is equal to a plus jb. Okay, this is one root where a is the real part and b is the imaginary part. So I mean to say, so the real part of this complex root should also be negative. Okay, we'll come on to this also, that how do you compute it mathematically. Now it would be beneficial for you to also see that what we are speaking about the disturbances by a video as well. That just a small introduction about this Tacoma Narrows Bridge, which was built in 1940. It was built in Washington DC in the US. So this bridge was constructed at that time, and because of the heavy wind flowing across the river, this bridge was collapsed. Okay.
Dawn of a fatal day, and the wind begins to speak with a roar that no man can fail to hear. In a 40-mile-an-hour gale, the center span weaves like a ribbon in a swinging twist that you wouldn't believe possible unless you could see it as you do now. There's an automobile caught on the heaving roadway.
So basically this is an actual bridge. Okay, and it is because of this wind flowing across the river, it is being distorted very heavily.
The 11,000-ton center span twists and strains the giant cables that support it. Cables of 6,300 wire strands, each 17 inches thick. Back out of the danger zone, all stricken spectators are driven to safety as the bridge gyrates like a nightmare high above the river, twisting, turning, curling. The lone motorist is forced to abandon the car. He has but a few minutes in which to save himself. Face to face with fate, his destiny hanging in the balance. Will he heed the last warning or perish with the doomed structure? But he saves himself by seconds. Engineers are divided as to the cause of the disaster. Some claim it was the use of solid girders, others differ.
So were you able to see that how this oscillations or the, let's say, the disturbance on the overall system has crashed the bridge. So now try to think that where the control loop is coming here, okay, where the control loop is coming here, okay, this is left as an exercise. Try to think that how, where the control loop is coming here. And because if you just Google about this bridge, okay, this you can easily find on the Google that this bridge has been constructed obviously newly, and this is now operating very effectively. But that time when it was constructed, because of this, because they did not take into account all the disturbances, this bridge was crashed, and this could happen easily. Okay, and also try to think that when that disturbance started acting on this bridge, we saw that it crashed. Okay, we saw that it. But what was, or let's say, there is a very basic key idea that why or let's say the very basic reason that why it has crashed. Okay, all these things will start getting clear to you when we speak about the frequency domain. Okay, when we start speaking about the stability in the frequency domain, just remember this example, which was that variable which we need to take care of when there are oscillations started in the system. So the basic concept we have already discussed, that when a process is disturbed, so what we will be studying in this whole lecture, when a process is disturbed from an initial steady state. Now this point comes into the picture here, the steady state. What is, first of all, a steady state? Say by implementing a change in the input forcing function. The second thing comes the input forcing function. What are these input forcing functions? It will in general respond in one of the three ways. Response 1, we have seen that proceed to a steady state, and remain there. Fail to attain a steady state, oscillations and unbound, or increasing to the amplitude is increasing to infinity with the time. Fail to attain the steady state oscillation because the process oscillates indefinitely with a constant amplitude. At, at this current time, we have a basic idea now that this system, the very first one, okay, this one, we know, can I draw the box? Okay, so the figure A, this one, figure A, at this time, or at whatever we have studied, you can say that this is a stable one, this is an unstable one. But what about this one? This will also speak about that what type of stability is this one and how do we define it. Okay, though we haven't seen so far how you define these two things, but you have visualized. Okay, you have visualized so far that when do you call it a stable or unstable system, right? So to first of all, we'll see when do we call a steady state, or what state we call a steady state, by considering this very basic example, a simple pendulum. Okay, this is a simple pendulum which you can also observe in your hanging wall clock. Okay, where you see a pendulum. Okay, I have this I theta double dot. Okay, this is a single equation you get, and if I move this one forward here, mgl sine theta, I omit the t, the variable t, because here the theta is varying with time t. I guess we were connected by the time when I come to this equation, the third one. Let's say the one, the second, the third. Okay, so this is the single equation which defines the equation of motion under this case of heavy damping. Our assumption, what we assume. So the single equation defines the motion of this pendulum under this special case of heavy damping. So the final equation, what we have seen there. Okay, now what has been done in this equation? Let's first visualize it here. So what I just replaced. Okay, let's erase this ut minus mgl sine theta. Let's write this equation once again, equals b theta dot. Okay, now here I introduce the variable x, where I replace theta by x. Okay, and we call it a state variable. Why? For the moment, just assume that within this equation, okay, within this equation, The dynamics are basically defined by the differential of this variable, okay, and whatever the variables describes the dynamics, you can consider them inside the internal variables, which are called basically the state variables. Okay, we'll come on to this maybe a bit later when we speak about the state variable representation, but for the moment assume that I replace this theta x just to visualize that how the state of this simple pendulum is behaving with the input mgl sine x dx dot. Okay, when I put this u to 0, meaning to say I do not give any external input to this motion, just a free flow motion with some initial condition, right? Initial condition meaning to say with an initial theta which is not 0. Okay, so if you visualize only this equation, this equation gives you this plot. Now when you see this graph, which is basically a sinusoidal function, okay, we say now we are in a good state to speak about the steady states for the system, and the steady state meaning to say whenever the x dot variable is 0, whenever the x dot variable is 0, whatever the values we get for the x are defined as the steady state. So here at 0 we have a steady state, at pi or at number of n pi with multiples of n we have a steady state. Okay, so when we first define the steady state, we see the stability of those steady states only, because ultimately your system will going to settle down at those steady states. Yes, okay, just to clarify one thing, I have some students here, our students who are sitting in the classroom as well. So they have a question asking whether the steady state is equal to the equilibrium point. Yes, the steady state and equilibrium points are the same. Equilibrium point defines what? That the system will be at equilibrium. The system will be at equilibrium, or the system will going to stay there for its entire time. We'll come on to this later. Okay, right? So next we see that there are two equilibrium position what we have identified. Let's say only within the 0 to pi axis we have a equilibrium position of the steady state at theta is equal to 0, at theta is equal to pi. Now we need to see, or obviously you can also see by yourself when you have a simple pendulum, that what would be the stable steady state and which one would be the unstable steady state, right? All these five figures basically defines the motion of the simple pendulum, that if the initial angle is 0 degree, there won't be any motion, the system will going to stay here for its entire life. Okay, when you have an initial angle of 45 degree, okay, it will have some small amplitude which is defined by this small red graph here, how this will move. Okay, similarly for 90 degree you will have more swings, but ultimately it will going to settle at 0 degree, right? Similarly for all the rest angle except the 180, though we computed that we have a steady state at theta is equal to pi, okay, and we know that the system can stay there, but the system, if you can also visualize by yourself that the system is not able to stay there at 180 degree. It will fall down if you give an initial angle of this one, it will fall down to 0 degree, meaning to what? Okay, now come back to this the graph which we plotted earlier. When we are at 0 degree, okay, we'll stay there. Okay, it is quite clearly visible. When we move away and we haven't reached to 180 degree, if I give the initial angle at this point, it will always tend towards the 0 degree, right? In fact, but if I am at 180 degree, okay, it won't converge there, it will diverge to its implicit stable position, either 0 or 2 pi. Of course 0 or 2 pi, it's just a rotation of 2 pi degree. Okay, you can also visualize the stability from this graph as well, that once you start plotting this x and x dot graph, Okay, whatever the steady states you have identified, if you go just, if you are in the neighborhood, if you are in the neighborhood of this steady state point, you could see if you are approaching to that steady state point or not. If you are approaching that steady state point, meaning to say that steady state point is implicitly stable. Okay, if you are not converging there, if you are not converging there, that steady state point is an unstable steady state point. Okay, so I suppose now the concept of steady state is clear, and why we are studying the stability of the steady state. And let me tell you once again that whatever the special case we have encountered here, okay, I'll come on to this point later. I was about to speak about the linearization. Now comes the definitions of stability, that how you define the stability. We'll see the number of definitions of stability, but in the very general one, which apply almost to all the definitions which we will going to see now, was defined by Lyapunov. So we define the stability in the sense of Lyapunov, that a system steady state. Okay, I'll slowly read this statement. A system steady state XS. Okay, we have seen that what you call a steady state, okay, is said to be stable if for each possible region of radius epsilon which is greater than 0 around the steady state. Now go back to this one so that you can also visualize. I have a steady state here, right? I have a steady state here. Okay, if I go in the neighborhood, like it was said, if I go in the neighborhood of this one, epsilon greater than 0 around the steady state, there is an initial state x naught at t is equal to t naught. Here assume that t naught is equal to 0, falling within a radius delta. Basically delta is also a function of epsilon. Delta greater than 0 around the steady state, that causes the dynamic trajectory to stay within the region defined by this for all time t greater than 0. What does this stability definition speaks about? Let's see these two figures, what has been drawn here. We have this x1, x2, assume that we have the two states, x1, x2. Okay, so whatever the on the left hand side, the figure was basically the cross section of this one. So if you try to see the figure from this side, if you try to see the figure from this side, you will see this left hand side figure. So basically this is a cross section of this one. So what it says, if you have an initial state x naught, okay, if you have an initial state x naught which is inside this delta region, if I start at this point, then for all times t greater than t naught or 0, I won't escape this region which is of radius epsilon. If I start in this region and stay for my entire life in this region, then the system is said stable in the sense of Lyapunov. This you can visualize the in the time axis as well, that this is the delta region, this is the epsilon region. So you start here. So the ultimately at when t tends to infinity, you won't escape this cylindrical tube. That when we call the system stable in the sense of Lyapunov, there is a very generic definition of stability which applies to linear system and to the non-linear systems as well. Now we will see a couple of definitions so that we could converge to our study of stability for linear systems. Now there is another term called the asymptotically stable system. Okay, it is also in the sense of Lyapunov, that a system steady state XS is said to be asymptotically stable if it is both stable. Okay, we have seen when we call it a stable, and in addition there exists a region of initial conditions of radius delta naught, which is also a function of x epsilon, around xs, for which the system approaches xs as t tends to infinity. So you see the difference between this definition, the terminology of stability and asymptotic stability. The stability says that you will stay within that region. It does not guarantee, okay, you will reach that steady state. It says that you would stay around that steady state. Asymptotically stable system says that you will reach to the steady state. Definition 3, a system steady state is said to be unstable if it is not stable, of course. All these three definitions applies to general systems. Either it could be a linear system or it could be a non-linear system. Now we'll start converging to the or to see the variants of these three general definitions to the linear systems. So first we'll see when you can say that a signal is a bounded signal. So this would help us to define the bounded input bounded output stability, that a continuous time signal is bounded if there exists an m such that for all t belongs to the real number r satisfy this condition. Okay, if it is satisfy this condition, the signal xt, we say that the signal is a bounded signal. Now the stability, this bounded input bounded stability, if in response to a bounded input, my input is bounded, the dynamic trajectory of a system remains bounded as t tends to infinity, then the system is said to be stable, otherwise it is said to be unstable. I have a system, okay, what does it says? I have a system, okay, I have a signal ut, the input, I have a yt, okay. If I give a bounded input which satisfies this bounded criteria to this system, if my output stays bounded, okay, I have a bounded input bounded output stability. But do not forget that it is just a sufficient for linear system, it is not necessary for the linear system, meaning to say once you have defined, okay, you can only speak about the bounded input bounded stability. Whatever the very first definition what we have considered in the sense of Lyapunov might not be applicable to the bounded input bounded output stability. Okay. Now it says a system is unstable if any bounded input yields unbounded output. It just speaks about the boundedness on the input and output. Asymptotic stability for the linear systems, which you can also visualize from the second definition when we define in the sense of Lyapunov, what it says, an LTI, a linear time invariant system. We have a system. Now we are not speaking about the system in general. So now we'll see the feedback structures, so that whatever the definitions we have discussed so far could help us to actually compute the criteria to determine the stability of our feedback structures. Okay, so first we'll see this basic structure. We have this, the G naught, what we call the plant. Okay, first of all, forget about all these inputs. Okay, the DI, DO, DM, right? Just try to visualize. We have a simple closed loop with the external input RS. This is the external input which a user gives, okay, to this closed loop. Why I'm calling it a closed loop? We have a G naught, I have a controller which you have designed, then you fed back this output to the input of the controller. So this basically forms you a loop which we call a closed loop. So if you try to visualize in this one, we have a system, right? You give the RT, okay. We can draw this in this way as well. You have a plant, you have a controller, you have a output Y, okay. This is the input of the plant, and this output is fed back to the controller, right? And this system is basically what we call the closed loop system. So here they are defined in terms of as a function of S, which are the Laplace transforms, and we specifically define there is a set point, the control signal, and the plant output. We have other three variables as well, DI, which is the input disturbance, the output disturbance, DO, and the measurement disturbance. Okay, these are the disturbances over which we do not have any control. These are the inputs over which we do not have any control, or okay, but over this input RS, it is given by the user. So over this, we know what we are giving to the system, right? And this X naught, you can visualize it as the initial state of the plant. Okay, meaning to say, if your G naught includes any integrators, okay, these are the initial values for those integrators, X naught, which you could define as some function. Okay, So this is the what we call the 1 degree of freedom architecture. Why? Because here the user define only this part CS. We have only 1 degree of freedom to design the controller. Okay, this C of S is defined as a ratio of P over L. We have a G naught which is defined over the ratio of B naught over A naught. Okay, there are some couple of requests for interaction we'll take in the next 5 minutes once we discuss this feedback architecture. So if you start writing the equations for the output and input of the plant. So now the first question arises here, why I am only concerned with the input output of the plant? Why not? There are other signals also. We have DI, DO, DM, U, E, R, Y. Like I said, the RS is given by the user. Okay, it's you who give the set points to the closed loop. You have the other disturbance variables over which you do not have any control. These are the free variables, what you also call, these are the free variables. And now if U and Y are stable, okay, if U and Y are stable, this will eventually give me the final stability analysis for the closed loop that my system is stable. Okay, are you able to visualize this one? R is given by the user, the set points. Di, Do, Dm are the free variables. Okay, the initial value or the initial value for the plant is implicit, is inherent within the system. Now the only two variables which remains U and Y. If these U and Y, of course, this E is nothing but the difference between R and Ym. Okay, if you are able to say that your U and Y are stable, then your whole closed loop system would be stable. Okay, so that's why I start writing the equation for the Y and the U. So first visualize this equation Y of S, the Y of S, which is what? Since we are considering the linear time invariant system, you can neglect one signal, you can just consider one signal except the other signals and then sum them up to see the total response. Okay, so I have this Y of S. If I neglect this one, and this one as well, I have a US into G naught of S, which gives me one component of YS. Another component is coming from DO, the output disturbance, summation with this loop, this forward path, DI into GO, plus if this initial condition, I can write this as a function of S and X naught, right? This X naught is just a value, but it will still pass through the plant. So I can write it as a function with a denominator, so that this overall becomes a rational transfer function, because all these functions are rational transfer functions, right? And this F is a polynomial. So this is for the Y of S. For the U of S, we have the straight away CS, CSRS, and CSY of S, CSY of S, and another one coming from the disturbance from this path, from this, okay, from this path, from this path, and from this path. So all these three components give me the U of S. So I have a variable Y of S here in the second equation. If you substitute this Y of S here, it will give you this final equation. Okay, similarly you could put this U into U of S here. You would get your Y of S in all the external variables, right? And the external variables are what? R of S, DI, DO, DM, and this initial condition. So this is what it has been computed here, U of S and Y of S with respect to all the internal variables, R, DM, DO, DI as a function of X, R, DM, DO, DI as a function of X. So now here you can also see that why it is called a 1 degree of freedom controller. We have a number of, if I sum them up, I have an external set point, the R of S, okay, and the other variables are the disturbances, and I have only one controller, right? I have only one controller. So this controller either can give you the desired response with respect to the set point, or the desired response with respect to the disturbances. So if you have designed your controller such that it is giving you the desired response with respect to the set point, this gives you a unique response with respect to the disturbances. Or if you design this controller CS with respect to the D of S, it will give you a unique response with respect to the R of S. You have only 1 degree of freedom. Either you design your this single controller to give the desired response with respect to the R of S or with respect to the D of S, with respect to the disturbances. But just visualize, just write these two transfer functions from ys, the ratio of ys over rs and the ys over dos. Okay, just write these two functions so that we will see that how these two transfer functions will help you to determine the stability later on. Okay, we'll come on to this degree, the 2 degree of architecture, a couple of while. Let's take some interaction session or some questions we have. Hello, IGC EPJB Jagriti.
Hello, are you audible, sir?
Yes, I can hear you. If
Hello.
you speak a bit louder.
A very good morning to you, sir. I am
Morning.
Sujata Sharma from Indo Global College of Engineering.
Mhm.
Hello.
Okay. Yes. Yes.
Hello,
Ask your
sir.
question. I can hear you.
Okay. I am Sujata Sharma from Indo Global College of Engineering, and
Okay.
I would like to ask you a question. And my question is, how we can interrelate the theory of stability with the actual working of a machine?
With the actual working of the machine.
Yes, sir.
So this was the that this is the that's why we consider these two basic examples in the very beginning. The very first one about the governor.
Yes, sir.
Okay. I will come on
Can
to
you
this.
please
So the very
elaborate
first
that?
yes. So on the very
Yes.
first example, we consider about the governor, where we speak about how from where the stability analysis is originated. Okay. And
Yes,
now the
sir.
second example was a simple pendulum example. Since we have
Yes, sir.
written the equations for the simple pendulum, let's take a quick look to those uh, simple pendulum equations.
Yes, sir.
So this is basically a machine. You can also think of it as a machine, right? So when you see a machine, you start writing the dynamical equations for the motion of that machine.
Yes, sir.
Okay. So once you have the equations for the motion of the
Yes, sir.
machine, then you identify
Yes, sir.
the variables,
Yes, sir.
that which variable you want to control and which
Yes, sir.
variable are your control variables. So there is a distinction between the control variables, the disturbance variables. Okay, okay.
Yes, sir.
So if you
And
see
sir,
this,
and sir, actually, first we do analysis on stability for the first
mhm.
some years. But is it same analysis is applicable for after some 5 years or something for a particular machine? Is it applicable with the
Okay,
previous analysis of stability?
yeah, this is a very interesting question. Of course, it is difficult to say, but I would say that
Yes, sir.
the control engineer should do a stability analysis at a regular interval. And the
Yes,
reason for
sir.
this, because once we write the equation of motion for a machine, this
Yes, sir.
equation contains some variables, some parameters, okay, some constant parameters of that machine. Say for example, in the simple pendulum, we have the mass, the length, and the friction coefficient. Okay, as the life cycle of the machine pass on, these parameters can change. Okay,
Yes, sir.
these parameters can change, and once this parameter will change, you will have another dynamical equation which is completely defines a different dynamics which you have used previously for your stability analysis, right? We haven't
Okay.
so far analyzes the stability. What we are seeing so far, that how you define the
Yes,
stability
sir.
and with respect to the equation with respect to the steady state, right? So once we'll start taking
Yes,
this
sir.
topic of doing the stability analysis, you would see that how these parameters of this machine comes into the picture. Okay, so these
Yes, sir.
parameters will change over the time with the life cycle of the machine, or with the life or with the time span of the machine. Once this parameter will change, your stability will definitely going to change. Okay,
Okay.
so as a good control engineer, you should do a stability analysis at regular intervals.
Yes, sir. Okay, thank you for the answer. Nice talk.
So there's a question from ITM PJB. It says that I say that there is no effect or disturbance on stability. No, I did not say this. Maybe there was some miscommunication. So I did not say that there is no effect or disturbance on stability. In fact, the video we have seen there, where there was a heavy wind flowing across the river, the bridge was crashed, right? And that wind is basically a disturbance. So now in the 1D of architecture, what we have just seen, we have seen a number of external variables. Among those variables, some are disturbance variables, and the other variables are some input variables, or input variables in the sense the set points. Okay, so I said that you have only 1 degree of freedom to satisfy your desired specification, either with respect to the disturbances or with respect to the set point, right? It was so the disturbances, you are right, the disturbances are generally uncontrolled, meaning to say they are free variables. You do not have any control on those variables. Generally, these disturbances, okay, it depends on your assumption as well. Okay, you can consider the disturbances as bounded disturbances, right? As bounded disturbances also, okay, while doing analysis. But this is just an assumption. Okay, generally these disturbances are the free variables over which you do not have any control.
My name is Chandan Kumar from Indo Global College. My question is
Mhm.
why stability depend upon degree of freedom?
Okay, so at this point, make yourself clear that the stability does not depend on the degree of freedom, not at all. Why we are studying these different architectures? Just to compute, just to visualize that once you define the controller, because when you do your stability analysis, you also in the second step, or as basically in the first step as well, you design your controller, then you check the stability of the closed loop. Okay, so what we are discussing here, that what are the various different feedback architectures for studying the stability, right? The stability does not depend on the architecture. The stability only depends on the closed loop. In fact, not on the closed. Let me rephrase the statement. The stability, the stability analysis, what we do for the closed loop. Okay, such so that whatever the controller we have designed, when we put that controller in the closed loop, my overall closed loop system is a stable system. Okay, there's a question from MECMH: how you represent disturbances in the form of equations in stability analysis? Okay, how you represent disturbances? The disturbances are generally the variables. So when we start writing the transfer functions, we generally write as the ratio of the output variable and the input variables, and this input variable could either be your set point or could be the disturbances. Okay, this question from RCPITMH: what is the meaning of undamped and overdamped of control systems? Okay, this question is a very quick question. We'll come on to this later on, the study of this undamped or overdamped systems. Okay, basically these are the transients of the transients of the system, right? And here what we're discussing mainly the stability without going into the transient response of the system. Okay, but somehow possibly we'll see at some point about this underdamped overdamped systems. Sukhpal Singh E, what are the methods to improve steady state stability? Okay, we haven't so far discussed the tools to do the stability analysis. So we can see the methods in a couple of while. Okay, this is the last interaction I am taking now. After that, we'll take the interaction at the end of this lecture, today's lecture. So before the break, we left off at this point where we were discussing about the 1 degree of freedom architecture. Okay, and I also wrote down these two transfer function. Okay, so here what you have seen, we have a ratio of the output and the set point, the R of S, in one transfer function. In another transfer function, we have a ratio of the output and the with respect to the output disturbance only. Now let's quickly see this 2D of architecture. So what we have done in this 2 degree of freedom architecture, here we could shape the references and the disturbance rejection separately. So what we did, we put a H of S on the transfer function just before the R of S or just after the R of S. So here we are designing two two transfer functions, C of S and the H of S, and how it helps us to shape the references and disturbance responses separately. We'll see when we write the equations for the output and input of the plant. So this is the output variables, and these are all the transfer functions with respect to the RS, the output disturbance, the input disturbance, and the measurement disturbance. Okay, so now just give a close look at this equation, that this H of S transfer that this H of S transfer function appears only in the path when I am observing my output with respect to the reference. Okay, while C of S is coming in all the transfer function with respect to either with set point and disturbance. So the what I did, I took an approach where I designed this controller C of S such that it shapes the response with respect to the disturbance. Okay, and then I designed my H of S such which gives me the desired response with respect to the R of S. Okay, here I am designing two transfer functions, C of S and H of S, so that I can shape the reference and disturbance responses separately. Now we will see that why these such kind of transfer functions I am looking for. Where are the stability properties are hidden in these transfer functions. H of S can be designed to shape the disturbance response, and the H of S can be used to shape the reference response independently. Okay, and now this is what we call the gang of four, all the sensitivity functions which are basically necessary when you start doing your stability analysis. So all these sensitivity functions are defined as nominal complementary sensitivity, nominal sensitivity, nominal input disturbance sensitivity, and nominal control sensitivity. Okay, all these four transfer functions. So if you want to study the stability properties of the system, you need all these functions. So this was pretty much clear. This one, the nominal complementary sensitivity G naught Cs 1 plus G naught Cs, the ratio of here what you will see very quickly, that this is nothing but just a closed loop with the controller in the loop, and this is the ratio of the output and the set point, and this nominal sensitivity is the ratio of the error and the set point. Now if you recall, your error is basically coming is this side, this is the error, and all these four transfer functions are written with respect to the 1 degree of freedom architecture. So this E of S, so the ratio of this E of S and R of S gives you the sensitivity function, the nominal sensitivity function, and you would also see that if you sum them up, T naught plus S naught will give you 1. Okay, there are some properties, initial properties, but these are four sensitivity functions which you require to do your stability analysis, and how we'll see in the in the 2 degree of architectures. In this slide, we have some other transfer functions as well, the two bottom transfer functions with respect to the initial condition. So all this Y naught and U naught, which are basically the output of my closed loop systems. Okay, you can write this in this form, in the matrix form. Okay, where this where the denominator remains same for all these transfer functions which are the numerator. Okay, this is the matrix forms of all these two equations what we have seen earlier, to which the denominator. So the important thing to notice here, that the denominator transfer function for all these transfer functions is same, which is given by 1 plus g naught cs. Now here comes our lemma, which says the nominal internal stability. That consider the in fact any closed loop, any nominal closed loop, not necessarily the 2 degree of freedom. Okay, consider the feedback closed loop with the model and the controller defined by the representation given by these two, which we have seen earlier, the GFS and the CFS. GFS is our plant, the CFS is our controller respectively. Then the nominal closed loop is internally stable if and only if the roots of the nominal closed loop characteristic equation, this one, if the roots of this equation lie in the open left half plane. Okay, this is the result. And from where do you get this result? Oh, basically from where do you get this equation? So if you see the g of s, which was what, b naught over a naught, and c of s, which was p over l, and we have seen that there was one common thing in all those sensitivity function is the denominator, which was given by 1 plus gs cs. So let's write this thing, 1 plus gs b naught over a naught. So this give me a naught l plus b naught p divided by a naught l. Now see that this is in the denominator. So the numerator of this will go into the denominator of the sensitivity function, right? And the denominator of this will become the numerator of those sensitivity functions. And this equation is called the characteristic equation, and basically this is a polynomial. Okay, do you see the difference between the polynomial and a transfer function? Transfer function is a ratio of two polynomials. Okay, here I have one polynomial, here I have another polynomial, and this polynomial is a denominator of those transfer functions. Okay, so this is also called the characteristic equation, and if I equate this equation to 0, characteristic equation to 0, then that result says the roots of this equation, if they lie on the left hand uh, side of the S plane, okay, then your system is internally stable. Let's see this. So how do we prove this? That the nominal closed loop is internally stable if and only if the roots of this characteristic equation lie in the left plane. So we'll start our analysis. So first, what we'll start with, first we show that if all the poles were negative real part, okay. If you recall from the very first S plane I have drawn, there were real axis and the imaginary axis, and I was saying that if the even if it is a complex root or a real root, I am concerned only of the real parts. So first we show that if all poles have a negative real part, then the system is asymptotically stable. Okay, so let's write the transfer. Okay, so we'll take this window. So let's write the g of s, which is represented by a numerator polynomial in terms of s, and in denominator we have this s minus p1, s minus pn. We have n poles, and we assume here that the poles of this gs are distinct, that is to say that the denominator has no repeated roots. Of course we can remove this restriction later, but let's see this for the assumption. So this I can write in the form of for naught after doing the partial friction, okay. This is my g of s. Now if I take the inverse Laplace transform of this g of s, I will get the g of t, which is given by alpha naught delta t, okay. So now these p I can write, these are the complex variables. So I say let pk is equal to sigma k plus j omega k for all values of k, for all values of k equal to okay up to n, right. So let's see this now. Okay, what do we write? Let's see all the components. If I put this p of k into this e to the power in the exponential thing, let's write this e pkt and take the mod of it. What I will get is sigma k plus j omega k. I forgot the t. Okay, this I can separate e to the power sigma k t and e to the power j omega k t. Okay, and this part is equal to 1, right, from the basic properties. So this eventually will give me e to the power sigma kt. And now see the mod of this gt. So what it will give me is, if you take the mod of this gt equation, right, if I take the mod, sorry, in the next step, what you will do, you take the mod of this one of gt on both sides. So what you can write, that the g of t, if I separate this, would always less than your alpha naught delta t plus alpha 1 e to the power sigma 1 t. Okay, now we see separately the integration of the exponential power. If I integrate from 0 to infinity of this exponential e to the power sigma nt dt, what I will get, which is equal to minus 1 over sigma if sigma is less than 0, and infinity if sigma is greater than equal to 0. Okay, so basically the why I'm doing this, so because I need to compute the integral of this mod of got. So if I take the integration of this, the first equation, what it will give me is alpha naught plus alpha 1 over sigma 1 okay. And basically this is what, here I assume that sigma is less than 0, that's why I'm getting this over sigma 1, otherwise this will give me the infinity. Are you following what I'm doing here? That why I take the integration of this one, so that if I take the integral of this exponential, because I want to compute the integral of this mod of g of t, right? So I compared this exponential thing, I substitute it here, owing to the condition that all the real part, this is my previous assumption, that all the poles of the real parts have the negative values, and this is a finite value. This is a finite number. So which will eventually, which give me finally g of t dt, and this is what our definition for asymptotic stability. that if the impulse response satisfy this condition, then I define my system as stable system. So we have proved that if all the poles have a negative real part, then your system is asymptotically stable. Okay, and we also assume that it is for the distinct root. Now this is left as an exercise that if you have a repeated roots, then I say that the same results hold. Okay, then you can see by yourself, assuming you have a repeated roots, and then you can prove in the similar manner. Now if you recall, we have said that the nominal closed loop is internally stable if and only if the roots of this equation lie in the open left up plane, and we have only shown the if statement, not the only if. Now we show the converse. If we are able to show the converse, that gives us the if and only if criteria. Now we show the converse, that is, if a system is asymptotically stable, then all poles have a negative real part. Okay, initially we have shown that if the poles have a negative real part, the system is asymptotically stable. Now we show that if the system is asymptotically stable, then all poles have a negative real part. So what we assume, that for all values of s, for which the real part of s is greater than or equal to 0, we have the mod g of s. Let's write the mod g of s 0 to infinity this one, where here is the Laplace transform and they're taking the mod of both sides. This would be less than or equal to what? If I take the mod inside, e to the power minus st mod g of t d of t. Okay, and this would be what? Be less than 0 to infinity mod g of t dt. Since we know that e to the power minus st will always be less than 1 for real part of s greater than or equal to 0. This will hold if I have the real part of s greater than or equal to 0, right? This will always be less than 1, equal to 1. Okay, and this, if my system is asymptotically stable, right, meaning to say that this is equal to what? A, which is a finite number. So this prove me the only if statement, and this says that if and only if the roots of the equation lie in the left half plane, my system is internally stable. In fact, the corollary, or you can say that as a corollary, that this amounts to say that the nominal loop is internally stable if and only if all 8 transfer functions are stable, basically these transfer functions, and all these transfer functions are basically constitutes the sensitivity functions as well. So we'll consider an example. So assume that we have this g naught of s given by this transfer function, the ratio of 3 over s plus 4 and minus s plus 2. We have a c of s, the controller, minus s plus 2 over s. I will ask you to compute the t naught. Okay, compute the t naught very quickly, which is nothing but the ratio of g naught c divided by 1 plus g naught c, so that you can see that your system is stable. Okay, compute it. So your t naught of s, what it will come, let's see here also. So the t naught of s is nothing but g c over 1 plus g c. I omit the s. Okay, what you are having? What is this t naught? 3 over s plus 4. So the denominator, okay, let's so the denominator, what is what you are getting, s square plus 4s plus 3, is it? And this you can write as what? S plus 1, S plus 3. And this is my T naught of S. So I can see, and this is the denominator. So I see that the denominator of this transfer function, the roots of this polynomial are lying on the left half side, left half plane of the S plane, meaning to say that this is stable. Okay, but what about the internal stability? If the system is entirely stable, for this we need to compute all the sensitivity functions. So we have the input disturbance sensitivity function is unstable, because if you compute this sensitivity function SIO within the gang of 4, you see that we have the pole here, we have the one pole which is on the right hand side, meaning to say that this system is not internally stable. You have to visualize all the 8 transfer functions, or at least the gang of 4, to see whether your system is internally stable or not just the transfer function from the set point to the output. So now the stability and problem analysis. Uh, so I would restrict today at this part, because now what we would be considering about explicitly, we will be dealing with the polynomial analysis. We have seen that finally, once we study the feedback structures within the LTI systems, okay, we come up with a characteristic equation, and this characteristic equation is nothing but a polynomial, right? So now in your hand you have a polynomial, and based on this polynomial you do the stability analysis. So whatever the tools I have listed out in the contents, then in the very first slide, all those tools will be applied on this polynomial, because this polynomial we have seen in that previous lemma that it gives a very strong result, that if I am able to prove that the roots of this equation lie on the left hand side, okay, this means that the system is internally stable. And we have seen in the initial couple of slides that this stability is basically an algebraic problem. How? We will see as a subsequent of this polynomial analysis. Okay, so if you see this polynomial, if you see this polynomial is a nth order polynomial. Okay, and in the initial couple of slides we have seen that Maxwell has proved that stability only up to third order system, and he posed the stability problem as an algebraic problem. Okay, so we will see that what are the different tools so that we can solve, or we can compute the stability for up to nth order systems. Okay, so now we'll stop today at this point. I can have some interaction session, or I can take some questions so far if we have any. So there are some interaction requests. I'll first take from Bina. RCP ITMH.
Hello, sir.
Yes.
I have a question. How resonant frequency can affect the stability of the machine?
Say it again.
How resonant frequency can affect the stability of machine?
The resonance frequency. Okay, this is again a very quick question, I would say, because when we'll start discussing about the stability in the frequency domain, taking this Nyquist criteria and the Bode plot, there this concept of resonant frequency will come into picture, and you would be able to try to relate that resonant frequency with the crash you have seen. So possibly we'll cover this thing in the on the third session, or maybe in the second session as the time permits. Okay, there was one question from IJCEPJB Jagrati. When we talk about the stability of a system, we always say that the bounded input has bounded output. Could you please elaborate these line Bibo? Okay, basically it was the one of the definitions of stability we have seen. We have also seen that when this input is bounded, and when I say that the input is, or let's say when a signal is bounded, we mean to say that the amplitude of that signal over the whole time horizon is less than equal to some some finite number. Okay, the signal should not tend to infinity. Okay, so when I, okay, can you please give an example of poles and zeros in practice? Yes, we will see some case studies and some examples as well, maybe in the session 2. So first we do the stability analysis using those polynomials, and then you can see, yes. So we always talk about effect of poles on stability. What is the effect of zeros on stability? Okay, well, in fact, this is a very good question. Yes, we always talk about the stability in terms of the poles, because poles basically defines the dynamics of the system, I would say. Okay, these things will become clear, mm, or these things will become more clear when we speak about the state space representation. Okay, and also in the proof as well. Okay, in the proof as well of the lemma, what we discussed, that this lemma gives only the result in terms of the poles. So in fact, this is a good thing, that your zeros have not to be have any constraints. Your zeros are free. So in the proof, you saw that we have a restriction on the poles only. It doesn't say anything about the zeros. So there are no constraints in the zeros. So consequently, the zeros won't affect the stability. Yes, DC, are you?
Hello.
Yes.
Good morning, sir. Sir, sir, for zero input, is it necessary that output will be zero?
For zero input.
Sir, for zero bounded input,
Yes,
the output will be zero.
the output will be zero. In fact, it is straightforward.
Output will
If
be
you
zero
if you
for
have a
zero.
transfer if you have a transfer function, right? If you have a transfer function as a ratio of the output and the input, and you apply the zero input, your output would definitely be zero in this transfer function, right? If you see those one of the transfer functions we saw in the 1D of architecture, the ratio of y of s over r of s, right? If you apply the r of s is zero without any disturbances. Okay, without any disturbances in that closed loop when with respect to zero initial conditions. So is there any pole zero cancellation? Yes, in fact, yeah, we haven't speak about explicitly about this pole zero cancellation, but you could quickly see in the example, in the last example, what we have seen in the controller, there was a zero in the controller whose root is on the right hand side of the S-plane, and there was a pole in the plant whose root is on the also on the right hand side. So basically there was a pole zero cancellation if you have a G into G into C, right? So this is what you call the pole zero cancellation basically. But yeah, maybe we'll speak about explicitly in the next session or maybe in the next after. Okay, how the system behaves if all the roots of equation lies at a far distance from the origin in the left half plane. Okay, well, this is also a good question, I would say, because if you see this lemma theorem, what we have just proved, the stability just says that the root should be on the left hand side. Okay, how far they are from the origin basically describes the transient properties of the closed loop. Okay, and here we are discussing only about the stability, the transient, not the transient response. So the location of the poles on the left hand side describes the transient response. What is the requirement in the transfer function? Well, this theorem gives you the final result. Okay, if the roots of this characteristic equations are on the left hand side. Okay, this is a test. Okay, so I think we will stop today's session, and so whatever if you have any more questions or queries, either you could post on the forum, and I'll try to take a look at them time to time. Okay, so okay, we'll see in the next session, right?